the acknowledgement of indigenous lands. Yes, absolutely. Through geoarchaeology. In fact, as I mentioned a little later, I like to refer to a lot of the work that we do as paleoeconomic geology. And in fact, it's very much focused on the indigenous peoples, many different groups who occupied the lands in Canada and the US, and their indigenous knowledge and relationship with the land. Absolutely.
Adrian suggests exchange and interaction between groups in the past.
That's a big one for sure. And from an academic standpoint, absolutely. And also, I guess, from an indigenous standpoint, in the sense that, it's sort of lays out the groundwork between and the relationships between groups living in various regions throughout the Great Lakes, of course, and throughout the Americas. Yeah.
Jackie also chimes in with trade patterns, which is similar.
Very much the same, but also it's interesting in terms of volume. There's a very interesting scenario that occurred, a little over 2,000 years ago that was, the result of a more industrialized group and its impact on former trade by other groups. But anyway, we'll leave that alone for now.
Oh, sorry. Mona would like the question repeated if that's possible.
All right. Well, I'm just asking if people can think of a question that concerning past human activity or worldview, which might be addressed through geoarchaeology.
Jessica suggests mobility patterns.
Right. Although that can be challenging in the sense of knowing whether long distance connections were direct or indirect through down the line exchange. But yeah, you can certainly begin to get a handle, that's for sure.
Andrea offers selection of raw materials for certain uses.
Oh yes, very much so. Yeah, that's sort of the paleoeconomic aspect of it. In other words, what do you use different rocks for and why?
Heather offers technical skills and knowledge and use of natural resources.
Oh, absolutely. In fact, a friend of mine has this old Ontario Department of Mines annual report where they're talking about a consultation meeting in northeastern Ontario. And it really makes me laugh because there's a segment where they're quoting an Indigenous person who's been interrogated concerning the location of metallic deposits. And basically he says, yeah, I know, but forget it. So, yeah, I mean, some of the discoveries over the last few years even that we've made with regards to location of particular rare rocks, minerals, indicate that Indigenous peoples, had an incredibly encyclopedic knowledge of the lands they occupied. In fact, I sometimes wonder, not to go on forever, but I sometimes wonder, like, how did they find these little resources, spatially limited resource sites? And you kind of got to think that anybody who's going across the land, whether they're hunting or gathering or whatever, always kept their eyes open. But at any rate. So is that about it for now?
Okay, so we get William says changes in settlement patterns with tool evolution.
Yeah. Geoarchaeology can speak to, again, the relationship of a particular group to a particular region. In fact, if you find that they're coming into a region with a toolkit that's based on exotic materials, it makes you wonder, are they newly arrived or exactly what's going on from a social standpoint.
Paleo-environmental changes and adaptation to change.
Yes, well, yes, absolutely. So one of the kind of no-brainers there is the fact that there are certain lithic source sites that are underwater now, but weren't 8,000 to 10,000 years ago due to the low water strands of the Great Lakes. So that speaks a lot to mobility, to accessibility, et cetera.
And Tiziana says material agency.
Right, exactly. What can you do? And you know what you want to make, for instance, as Tiziana would say, or be interested in terms of amphibolite. And why do you select that particular material as opposed to, say, other igneous and metamorphic materials for the production of groundstone implements? Yes. Well, I think I'll just launch on from there. So obviously, there are other archaeological approaches to studying lithic assemblages, including the process of tool production or technology, which may include experimental replication and use, combined with wear studies, as well as comparative morphology, which can involve sophisticated morphometric analyses of tools in 3 dimensions. Also, during the late 19th and throughout much of the 20th century, ethnoarchaeological studies have documented traditional indigenous lithic tool production and use. And just as a reminder concerning replication studies, of course, the 2 major pioneers back in the late 50s, early 60s were Francois Borde in Europe, in France, and Donald Crabtree in the United States. And I remember being an undergraduate at University of Toronto in the 60s. And Bruce Schroeder, who was a professor there, was working in Lebanon in the Bekaa Valley, which you wouldn't want to be doing anymore. And he was working on Paleolithic sites there, and he used to ship back huge crates of Lebanese chert, which was very nice. And he would hold these classes where students could maim themselves by practicing flint napping. And you know, that was my first opportunity, and actually I was a TA in one of his courses. And, you know, at that point in time, it really, you know, I was interested in lithics, but it gave me that opportunity to try to replicate tools and also work with others and watch what happened. And so as a result of that, you know, throughout the 70s and into the early 80s, I was quite an accomplished flint napper, you know, within a provincial context. But I have to say that quickly dwindled since that time, as many individuals have become extremely competent flint nappers. People like Dan Long and Darcy Fallon here in Ontario, and of course, hundreds and hundreds of others across North America. So I just want to give a shout out to those individuals and their abilities and how they can help us look at technical issues that our own competence does not allow. And then the ethnoarchaeology, just as an aside here, I'd like to go off on a brief narrative, if you don't mind, about the fact that in 1979, I was approached by Dr. David Rupp of Brock University, who was working in Cyprus. He wanted me to design a stratified random sampling design for 3 river valleys in Southwest Cyprus that would be statistically valid. And I thought I didn't have anything to do on the weekends anyway, so I did that. And then to my surprise, he invited me to direct the first field season using that survey design in 1980. What I did was I sat these 35 students from the consortium of universities down, and I flint napped, and I showed them what they could expect to find as a result of that. Now, the previous year, they'd been doing a judgmental survey and had bags and bags of ceramics, as you know, dear to the heart of classical archaeologists. So the next few weeks after my demonstration, they came in with bags and bags of debitage, much to the concern of the classical archaeologists who were part of the project. And I went out and had a look, and I see these 20, 30 meter scatters of chert flakes, and there were chert flakes, but there are no obvious hammerstones. There were no bifaces. It was hard to even find a core. So I was a little bit confused by this, to say the least, but luckily one of my crew members spoke perfect Cypriot Greek, and we began a process of visiting villages back up in the hills and mountains and asking people about this industry. And soon enough, we came across a lot of information, especially about the flint knappers who had been actually engaged in producing threshing sledges, which is, they were called tribuli by the Romans. It was Roman agricultural technology that was utilized by these villagers up until 1950. And so these gentlemen who were the master flint knappers, called Athkiakas Technites, there was only 2 of them left alive on the island, and we were so lucky to have met them. So there you see Michaelis, one of them, of the village of Panapaya, and one of his products, one of the threshing sledges with 400 chert flakes on the bottom of it, used for chopping up grain for the winnowing process. So anyway, it was a real eye-opener for me, and we were very lucky that we did document that industry. It was part of, was a master science thesis at the University of Minnesota by David Perlman. And frankly, of course, the master knappers are dead now, and no one seemed to be particularly interested in their trade in Cyprus. So it was a really lucky happenstance that we were able to document what we did. So anyway, let's get on. Right. So what I'd like to do is to try to show you these very brief videos. Let's see what happens here. Come on, guys. Nope. Okay, well, I'm going to just pass on that. Basically, what those 2 videos show, the earliest one, the geology one here, is the most important message out of that is the cyclical nature of rock generation, how igneous rocks composed of a variety of minerals, for instance, like granite, quartz, feldspar, and mica, can degrade into sediments and then be metamorphosed, etc. And so you've got a cycle. They can be further metamorphosed from the sandstone to materials like quartzite, etc. So I think it's the reason I threw that in there is I really wasn't sure of the range of knowledge. It's probably just as well I didn't show it to us. There's probably some professional geologists among the audience here, and that would be a little bit insulting. So anyway, I'll just continue on.
Would you like me to share the links in the chat, Bill, so people can watch it later? Or
sure, absolutely,
okay.
Absolutely, that would be great. Thank you so much, Caitlin. So anyway, we're just going to go through some very standard rocks that you may well come across in your travels and on archaeological sites. This is a series of igneous rocks. This is gabbro. It's a mafic, intrusive, coarse-grained igneous rock. And again, as I was mentioning, there's a variety of minerals, clearly evident here, including quartzes, feldspars, etc. Hornblende, probably. Whoa, excuse me. Now I'm in trouble. Damn, all right. Okay, let's go. Oh, all right.
Is it stuck?
There we go.
Perfect.
I think I have to click it up top here. Okay, this is granite, as I mentioned before, and again, 3 minerals: quartz, feldspar, plagioclase, feldspar, biotite, mica, and basalt. Now, the granite is a felsic intrusive. It's got more silica in it. It's coarse to medium-grained igneous rock, and the basalt, as you can see, is a fine-grained igneous rock. It's mafic, and it's an extrusive. That is, it's a rock that is spewed upon the crust of the earth, oftentimes by volcanic activity. And one of the important things about the previous 3 rocks is that they have what's known as fracture toughness. And so while you can flake basalt due to its fine-grained structure, you're not going to have a lot of success flaking granite or the gabbros, but for certain uses, that's a good thing. You want to have fracture toughness. The next material, igneous material, is something that does not have fracture toughness and has a conchoidal fracture. It's a felsic extrusive and a glassy rock, which I think many archaeologists are familiar with, and readily flakes. And so it's not the sort of thing that you would necessarily want to use as a hammerstone or a heavy-duty axe, because they wouldn't last too long. However, if you want a really, really sharp blade to use in a very fine cutting activities on soft material, it's perfect. In fact, glass is used nowadays by plastic surgeons because the edges have a greater sharpness than surgical steel. It's even reputed that Don Crabtree actually made a series of obsidian blades for his own heart operation, but I'm not sure if that's really true or not. So we got into sedimentary rocks. We got limestones here, and we got, a chemical sedimentary rock composed primarily of calcium carbonate, and it can often be fine grained. We'll be talking about possible uses of these materials a little later. Sandstone, where you're looking at a clastic sedimentary rock composed mainly of sand-sized silicate grains. And greywacke, which is a poorly sorted clastic sedimentary rock. A diamictite, so you can get actual pebbles within the matrix that you would see to the left there. The illustration on the right is on the side of the Trans-Canada Highway north of Georgian Bay. And it's a part of the Goganda Formation, which is very interesting formation because you can see cobbles, rounded cobbles within that matrix. And in fact, it's what's known as a tillite. So what you've got is a indurated glacial drift that dates to the Precambrian period. And actually this raw material turns out to be particularly important to certain indigenous peoples to the south. So next we have our shales, laminated fine-grained sedimentary rock, various colors. We have siltstones, clastic fine-grained sedimentary rocks, again of various colors. We'll be talking about their uses later. And of course, hematite. And it's an iron mineral that's deposited in sedimentary and metamorphic rock. And the image to the right is the lost locality sample site, which we discovered a couple of years ago. We're working with the Ontario Geological Survey looking for a graphite deposit, which we eventually found about 100 meters from this outcrop. And the interesting thing about it is when it was geochemically sourced and compared with archaeological specimens from a Huron-Wendat site about 100 kilometers to the north, it was a perfect match in terms of the hematite. And interestingly, that same village site produced some of the most abundant graphite paintstone from any archaeological site in Southern Ontario or Northern Ontario, for that matter. And so the fact that the graphite source site seems to have been 100 meters from here is quite significant. So metamorphic, nice, of course, coarse grain banded metamorphic rock, often derived from granite. It has uses. It was used. In fact, one of the interesting uses I see regularly on archaeological sites, especially the woodland ones, is the disintegration of nice cobbles through firing. They're used as fire-cracked rocks, so-called, for heating purposes, but with continued heating, they disintegrate, and the components are I've crushed, I'm quite sure, and you'll find the same range of minerals in the temper of ceramics. So gneiss seems to have been quite a favored material to use in a disintegrated form for the tempering and production of ceramic vessels. Lorraine quartzite, this is a major tool stone that's found north of Georgian Bay in the Precambrian there. And it's a non-foliated metamorphic rock, consists mostly of quartz. In the bottom right, you'll see that it has, beyond white, you'll see green versions of this quartzite, same formation, Lorraine, and also pink, and also orange. So there's quite a rainbow of colors within this specific formation. And then we've got argillite, fine-grained metamorphosed mudstone that's often laminated. This turns out to be a particularly useful stone to indigenous groups, and we'll talk about that later again. And then we've got slate, which is a very fine-grained metamorphosed mudstone displaying foliation. So you can see you can split it in thin layers or layers of various thickness because of its foliation. And of course, you may recognize it as a roofing material. It was very popular in Europe and also utilized in North America for construction purposes. Slabs of slate, all covering church roofs and various institutional buildings. And then we have schist and amphibolite, which are foliated metamorphic rock that includes micas and chlorite. And steatite or soapstone. It's a soft metamorphic rock composed primarily of talc. And because of its qualities, it was widely utilized by indigenous people for a variety of purposes. So that's just our little run through of some of the rocks that were of significance to indigenous peoples. Oh, geez, here we go again. Pardon me. Come on. So our next map just gives you an overview of the bedrock geology of Ontario and adjacent states and Quebec. And obviously the orange and also the ochre yellow colored zones are Precambrian. The blues, the mauves are Paleozoic formations. Significant for our discussions of cherts obviously will be these formations. And so we've got formations running from the Ordovician through the Silurian, through the Devonian, in southern Ontario and up the Ottawa Valley and into Quebec, of course. And also there's a whole patch in the Hudson Bay lowlands up here of similar aged Paleozoic materials. And in fact, there's even some Mississippian post-Devonian material in this area here. And another thing that you should really note here is the fact that you've got the Michigan Basin here, and you've got the Appalachian Basin down here, and running through here is the Algonquin Arch, which separates the two basins. And it has quite an impact on the distribution of formations, at least certain formations, which had indigenous value, let's say. So, and again, the Paleozoic formations are primarily sedimentary, and of course the shield Precambrian materials are primarily metamorphic and igneous rock. So part of this Precambrian series of formations is the Huronian supergroup, which just by chance has a great number of significant rocks that were utilized by indigenous peoples. And they're, this Huronian supergroup sort of spreads east to west across the north shore of Lake Huron, Georgian Bay. And so there's quite a lot of use, as I say, by indigenous peoples of various materials. So for instance, the Bar River Formation up here produces some very fine quartzite that can be turned into bifaces and various other tools. Gordon Lake Formation includes cherts, which were utilized quite extensively during the Archaic period. The Lorraine Formation, it was also utilized. The quartzites there were also utilized for biface tool production, uniface tool production. Goganda Formation, well, it's got diamictites that were utilized for production of ornamental goods, such as gorgets, etc. And so this Upper Huronian series of formations were very significant to Indigenous peoples. There are other significant materials in the Lower Huronian, but not as many. There's actually a black pipestone in the Matinenda, I believe. We've got to locate it first, but we know it's up there somewhere. So hopefully, as soon as the pandemic allows it, we'll get out and looking for it. Anyway, so just by way of showing that there are some really substantial deposits of economically significant materials to Indigenous populations. And this is also to remind you that there was another major factor in the distribution of raw materials, and that was the various glaciations, the last of which was the Wisconsin. And if you look down at the terminal moraine location, the southern extent through Ohio and the Midwest, you'll realize that these sheets bulldozed raw material out of these formations in the bedrock all the way down to, again, mid-Ohio. And so that's been quite significant, because what happens is that I got contacted by archaeologists down in Ohio, and of course we're interested in the material being used to produce gorgets and birdstones and banner stones, etc., called Huronian banded slate in the old literature, and wanted to discuss, how that material is getting to Ohio. Well, they're saying, well, is it being, exported from the bedrock sources in northeastern Ontario? I said, I doubt it. I think all you've got to do is look in your terminal moraine and look for cobbles of the upper member of the Goganda Formation, the banded argillite, and I'm sure you're going to find it, because I found it down to Lake Erie within Canada, and that's almost certainly the source of most of the banded argillite that's being utilized for these ornamental artifacts. So, you don't have to postulate 1,000 kilometers of transportation of raw materials. You must always be aware, excuse me, in glaciated regions of the potential for secondary deposits, pebbles and cobbles of raw material that were undoubtedly collected by Indigenous people. And we had one really great example of that on Lake Huron at the Candu reactor site at the Nipissing Strand Line. There were a whole series of cobbles of various colors of Lorraine Formation quartzite on the former Strand Line beach. And there's a whole huge workshop based upon this raw material. And I think one of the fellows, picked up a potato bag sack full of artifacts from that Strand Line made of various multicolored Lorraine Formation quartzite. And that's a real lesson that, when people tell me, oh, I got a white quartzite biface from Bruce County and, south shore of Georgian Bay, eastern shore of Lake Huron. And boy, I guess there must have been trade with the North Shore of Georgian Bay. And, you just sort of go, maybe, but not necessarily. So always remember that. So basically, we're going to look at some sourcing techniques here. And there's a few sort of major sources for some of the work. Some of the cherts that are found in Ontario and New York State and Michigan, Ohio, etc. So neutral activation analysis, or NAA, is one possible technique to utilize, but it's time consuming, it's expensive, and when you're faced with a bag of 1,000 chert flakes, you're sure not going to be utilizing this technique to identify or attempt to identify sources. The other interesting issue about this is that materials like cherts are not homogeneous, much as obsidian is, for instance. And so there's a considerable variability within formations and even within nodules of cherts in terms of trace elements, rare earths, etc. So it does create some problems in terms of utilizing this technique. Another one, it's much more quick and inexpensive and non-destructive, and X-ray fluorescence. And there are difficulties with certain trace and rare earth elements, as I said. It's great for obsidian. It's used constantly for that, since it really does the job of identifying and specific sources. But rhyolites and other materials like quartzites, not so good, again, due to variability within the formations. And you've got the issues weathered sample surfaces. EPMA, well-established technique. It's good, but it's destructive. The sample must be cut and polished to utilize it. Again, you're not going to be doing that with chert flakes. ICP and the use of mass spectrometers. It's not hugely destructive. It's quite quick. It's ideal for measuring isotopes. In the solution mode, though, it is quite a long preparation process using costly argon gas, as you can see. And not everybody has access to these kind of sophisticated analytical machines. And here's a range of other techniques for geochemical characterization. All of them have been utilized in one way or another with varying success. And I want to thank Dr. Brandy McDonald, who is an archaeometrist who works at the University of Missouri Research Reactor, for vetting my list of challenges to chert characterization, which you've just seen. And also mention that if someone wants to discuss any of these techniques in greater depth and detail, they'd probably be better contacting someone like Brandy or Dr. Adrian to discuss these issues, because they're far more aware of the technicalities than I am myself. So again, these are the issues with chert characterization, identification. In fact, just as an example, you can get something like Collingwood chert out of the Fossil Hill Formation in the Beaver Valley in southern Ontario, and you cut a thin section, have a look at the fabric of that chert, and you'll see that you have a microcrystalline matrix, sort of the original formation of the chert, but you'll get fissures and veins of flamboyant crystal structure of chalcedony, which is a secondary silica development within that chert. It's not general, it's quite specific and localized within the matrix or fabric of that chert. So again, these just add to the complications that I was just mentioning. And thin section petrography, important for determining or understanding the structure of the materials you're studying, not just cherts, of course, but any rock. And this, as I mentioned, in terms of Collingwood chert, it's very enlightening. It's not only enlightening in terms of fabric, but obviously it's enlightening in terms of micropaleontology, microfossils, which are very often very sensitive temporally, and can help you identify whether you're dealing with a material that's, say, Pennsylvanian or Ordovician or Silurian in source. So it helps you begin to narrow down sources for materials that you're studying. However, again, same issue. you got 1,000 flakes, you're not doing thin sections of all 1,000 flakes. So it's something that is of value. It can help you if you're starting to group your materials into types, which on the basis of visual inspection. And that's very important. It helps. My rule of thumb basically is if you're looking at an archaeological site which is dominated by one particular chert type, which is often the case, you figure out what that chert type is one way or another. Then anything that's not that chert type, in fact, something, well, as an example, you've got a site that's produced 10,000 Onondaga chert flakes and a couple of chert flakes that kind of look like Van Port Formation or Flint Ridge chert from Ohio. Well, you've got a site that's, again, say a couple of 100 kilometers from that source. Well, in that case, you might go to the trouble of trying various sophisticated ways of geochemically characterizing those pieces to say, yeah, it is, or no, it's not, if possible. So just before jumping into looking at various silicious materials that were utilized by Indigenous peoples, I just a comment concerning nomenclature as applied to, say, chert types. And that is that there's a tendency, or has been a tendency in the literature, for instance, Fossil Hill Formation, to talk about the Fossil Hill Formation chert from the Beaver Valley. And the thing is that the Fossil Hill Formation extends all the way from just south of Georgian Bay on the Niagara Escarpment, up the Bruce Peninsula, across onto Manitoulin Island, and into the Upper Peninsula of Michigan. And throughout that great length of the Fossil Hill Formation, there is chert types established in there, and they're visually different chert types. You don't need a great deal of geochemistry to show that they are different one from another. So if you're going to use a geological formation name for a chert, you kind of want to make sure that it doesn't have 4 different variants along the length of its exposure. And another good example of variance within a single formation is the Bob Lowe Formation, which I'll show a little later, where you've got 3 different, visually different, chemically different cherts, and geographically separated in some cases, cherts within that formation. And I guess one more thing I should say is that using visual identifications, for the most part, if an individual or researcher is familiar, I mean, minimum 100 hours with a microscope, looking at cherts and noticing their physical characteristics, the potential for microfossil inclusions, various color variations, translucence, et cetera, then even then, if you get a person who's not quite that familiar with the various cherts, you can get misidentifications, which have some fairly substantial implications to interpretation, as we mentioned at the top of the show. And that a great example of that was a report that was published decades ago, where it was a site in Bruce County, which is on the east shore of Lake Huron. And chert that was recovered from that site was identified as Ancaster chert, which derives from the Niagara Escarpment and the Hamilton area. And it's a Silurian chert. And the fact is there is a very visually similar chert right in the same area of Bruce County that happens to be a Devonian chert, Lower Devonian chert, which is Bob Lowe chert. And we call it Saugeen chert as a type. And so, there's a big difference in a site that's a couple of 100 kilometers from a source dominated by that source versus collecting local material in terms of understanding, obviously, movement, etc. So just a word to the wise. When you're dealing with visual identifications, you want to be dealing with individuals who have substantial experience concerning the range of physical characteristics of those materials. So anyway, this is a white quartzite lanceolate. It's from the Chagwinda Quarry site on Manitoulin Island, and it's Bar River Formation quartzite, as opposed to Lorraine quartzite, which is found just north of it. Bar River comes in only one color, the white, and as I indicated earlier, the Lorraine Formation is multicolored. The Bar River Formation quartzites are actually metamorphosed into mylonites, which are even better for flaking. And so some very fine artifacts were produced, particularly during the late Paleo period on this material. There's also rhyolites, and they're, again, not so fun to work due to their fabric. I just mentioned this because there's a series of cherts that I created a grab bag definition of on Lake of the Woods in northwestern Ontario, and I referred to Lake of the Woods chert. And there was sort of a translucent green colored material with phenocrysts, and there was black material that was quite homogeneous. And I was just finding these materials on Lake of the Woods archaeological sites. So, well, I didn't know where they came from. I figured it probably came from fairly close to Lake of the Woods. So, but subsequently, Patty Reed, who was the regional archaeologist out of Kenora, spoke to a geologist who told him the green material with the phenocrysts was actually a rhyolitic chert. Now that's an interesting, essentially a kind of a contradiction in terms, because, you know, officially cherts are supposed to be sedimentary and rhyolites are igneous. And so it's really not supposed to have igneous cherts. You know, knowledgeable geologists can correct me on that. But at any rate, there are materials that are very chert-like in terms of fabric that are rhyolites and equally workable. I ran into some in Mongolia in 2018. There's also other metasediments, such as this rather substantial biface, or fragments thereof, from just in the Kawarthas area of southern Ontario. And this material is definitely not coming out of a Paleozoic formation. It's coming out of the Frontenac axis of the Canadian Shield to the east. It's a metamorphic material, obviously, and obviously quite nice to flake. You can produce some quite large bifaces out of it, but we don't know where it is, where the sources are. But when you see things like this, you feel pretty certain that there must be some fairly substantial quarry sites yet to be discovered east of the Kawarthas and the Canadian Shield. So also Precambrian is this series of cherts, if you will. We've got the Gunflint Formation, which produces these tachynites here. Oops, sorry, I'll go back. At least I think I will. There we go. So there's a big boulder of banded iron formation, taconite, and there's a flake of that taconite material, which works very nicely, as you can see. Very much a favorite material for the earliest indigenous pioneers of the Lakehead region of northwestern Ontario, following the glaciers north. And this is another variety of chert within the Gunflint Formation. Interesting thing is that these cherts also contain 1.9 billion year old fossils, some of the earliest fossils in the world. And the Gunflint materials also, there's a carbonate chert. There's a what I call Gunflint silica, which is almost clear. And then there's a Gunflint jasper, which doesn't have this pebbled pellitic type structure here. So there's quite a few varieties within that particular formation. Another material that we found on the earliest sites in the Thunder Bay area was a what's called knife lake siltstone, and this is a biface, paleo biface base from Knife Lake. It's kind of amusing in a way because, obviously I realized that this was not an absolutely local raw material on these paleo sites in Thunder Bay, but I wasn't sure where it came from until I read a reference, a historic reference in the journal of Alexander Henry the Younger, and late 18th century, and his map of his route along the boundary waters between Minnesota and what is now Ontario indicated that there was, rather than Knife Lake, there was a Knifestone Lake, which, made me suspicious, and I was quite correct. There is just vast quarries and workshop sites on Knife Lake utilizing a turbidite sequence, so-called. So what you would get is you get volcanic eruptions, you get debris falling into water and settling out in differential rates, such that the lowest material, coarse material, was a gray whack. Above that would be finer slates, and above that would be finer siltstones. All these different materials have value and were quarried for different particular tool types. So let's get on to Southern Ontario. This is the oldest chert in Southern Ontario, what I call Huronia chert. There's no evidence of primary deposit utilization. All the chert appears to have been collected as pebbles in fields by local indigenous communities. I have no doubt that people who were out tending cornfields would just routinely pick up these shiny pebbles when they saw them and bring them back. And, I'd say 99% of the time they would work through bipolar percussion, just like cracking a walnut with an anvil stone below and a hammer stone above. And you produce, usable sharp flakes by that technique. It's not unique to the Huron-Wendat. It's been well documented ethno-archaeologically in places like New Guinea in the beginning of the 20th century too. So there's plenty of documentation concerning this particular reduction technique. So this particular Ordovician formation that produces Huronia chert is the lower member of the Gull River Formation. And, pebbles can get up to 5 centimeters in diameter. I've seen maybe 4 or 5 attempted bifaces made from this material within that region. And as I say, it's not optimum. The Balsam Lake chert is another Ordovician material from Southern Ontario. And it's from the upper member of the Bob-Cajun Formation. And as you can see, it's got a palitic structure here. It's quite distinctive in form. It's one of the reasons I have less hair than I used to, trying to locate outcrops of this material. It's very, very localized. So many, in fact, virtually all the Ordovician cherts occur as scattered nodules within a limestone matrix or a calcarenate matrix in this case. So, they're either there or they're not. And one of the interesting things when we actually found a source on an island on Balsam Lake, Grand Island, was that the nodules, you'll see one by the hammer there, were not just that thin within an outcrop that was, say, 10 meters in thickness, but the actual nodules exposed along that rock face would be, you'd find a nodule here and another a meter away and another one 10 meters away. So it gives you a sense of how difficult it is to identify bedrock sources for many of these materials, well, especially the Ordovician ones. Another Ordovician material is Trent chert. You can see what I was talking about in the bottom right image, limestone bedrock exposure, all those black nodules scattered through the limestone. You see a little more substantial deposit to the left. It's material, again, that was utilized primarily on the basis of secondary deposits. Anyone who's pounded away at the Bobcaygeon Formation from which this derives. It's actually from the lower member of the Bobcaygeon Formation, realizes that that limestone is not very friendly. And no indigenous person would be foolish enough to spend half an hour, 2 hours, half a day hammering a nodule out of that out of that bedrock. This chert, again, is not particularly thick, as you can see. It's up to 5 centimeters in thickness. The Balsam Lake is only up to about 3. And one of the things that's very interesting about this particular chert type is that there seems to be a real association with karst topography. So what I mean by that is that some of these karst features within the Ordovician limestone, such as various the Tyandanega caverns, for instance, you can go there and you go in the cavern and there's some really nice pieces of Trent chert in that exposure. You can go 100 meters to outcrop exposures all around that, and you will be very lucky to find one small nodule exposed. So there's an association which I don't understand with this particular chert type and karst features. It's also on the other side of the Frontenac axis, the Bobcaygeon Formation at the Bonnechere Caverns. Same syndrome. This is Kitchissippi chert, named by Quebec archaeologists, and it's essentially the same material. You can see it's a little more substantial in thickness in this particular nodule, but the same sort of Bobcaygeon Formation matrix. And it's available in the Ottawa Valley, especially around Hull in that region, Ottawa itself. Obviously utilized by local Indigenous people. Then when we get on the Silurian later formations in the Niagara Escarpment particularly, you get a variety of cherts, a little more substantial. You can see here some of the Collingwood chert from the Fossil Hill Formation. It occurred as 3 beds, and it's quite nice to work. It achieves thicknesses of up to 10 centimeters, and you get a certain tendency to banding within these cherts that you can see in the upper left, especially. Very light tendency, but it's still there. So, but as I said, the same formation on Manitoulin produces an entirely different looking material at Providence Bay. And then farther west, there's Detour chert, I call it, that derives from what is called, it's the same formation, but when it crosses the international boundary into Upper Peninsula Michigan, the Fossil Hill Formation becomes the Cordell Formation, for what it's worth. I'm sure it didn't make a lot of difference to Indigenous peoples who were collecting the raw material. So next on the Silurian agenda is Ancaster chert, so-called. Now, it has been identified over the last 40 years, 50 years, geologically as being from the Lockport Formation, the Goat Island Formation, and I forget what else. But anyway, there's a whole variety of formation names within which it was located, which again sort of speaks to the issue of using geographic as opposed to geological terminology. So at any rate, nowadays, and I was quite excited, Frank Brunton of the Ontario Geological Survey has redefined this Silurian sequence along the Niagara Escarpment. And so now this Ancaster chert is actually found in the Lockport Group, Goat Island Formation, and the Ancaster member. So isn't that a coincidence? So that was quite nice. The other thing that was a problematic situation for myself is that theoretically within the Lockport to the east towards Niagara Falls in the Grimsby area, there were cherts that were more lustrous, slightly different in coloration, patterning, and they're supposed to be from the same formation. So I was never very comfortable with that in the past. And then Frank told me, well, that's the Aramosa Formation now. Oh, well, that's great. So yeah, Grimsby chert is not from the same formation as Ancaster, although it has certain similarities. One of the big identifiers for a Lockport group, Goat Island Formation Ancaster member cherts, is the fact that there's a lot of silica in the body of these cherts, these nodules, that is derived from sponges. So you'll get actually some fairly nice sponge, larger macrofossils, but you'll also get lots of sponge spicules of silica from the sponges that were living in the nice warm seas where these cherts formed. So Ancaster, you get about 7 centimeters thickness. Now you may wonder why I talk about the significance of thickness of deposits as opposed to say the length of a nodule within a deposit. The reason I do that is that these siliceous materials get jointed through various motion of the formations over time, and the jointing basically terminates any attempts to drive flakes across these joints, these vacant areas within the formation. So oftentimes these deposits are so jointed that you really can't drive anything of any significance as a flake blank parallel to the bedding plane. So you're left to primarily utilize striking perpendicular to the bedding plane, which of course limits the length of your flake blank to the thickness of the deposit. That's not always the case, as Chris Ellis pointed out in his excellent dissertation concerning the Collingwood chert deposits in the Beaver Valley and their use by fluted point groups. Okay. All right, so entering the lower Devonian, we have the Boblo. En français, it's Bois Blanc, but it's pronounced Boblo through the influence of the corrupted French of the Detroit River region. There's a Boblo Island in the Detroit River where this material outcrops and where the formation got its name. Just a little tidbit there for you. Anyway, so this chert reaches thicknesses of around 10 centimeters. It's more substantial. And generally speaking, as you go through time in the Paleozoic, from older, i.e. things such as the Ordovician, formations like the Ordovician, through to later Pennsylvanian, Mississippian formations, which don't exist in Ontario, at least not Southern Ontario. And what you're getting is more and more substantial chert deposits. So at any rate, this is a bluey gray chert, and just above it is a lighter material. So it's a sort of creamy colored light gray material, visually quite distinct from the Colborne chert just below it. It's maybe a half a meter above the Colborne. And this was a very important raw material for high-low transitional paleo early archaic groups in Ontario. They seem to really trend towards this, I think, frankly, because of its color. And Bud Parker wrote a very good thesis on a quarry site, the Allen site, for Trent, based upon the Haldeman chert and quarrying and its use through time. The third type of chert that occurs within the Boblo Formation is Saugeen chert, as I mentioned earlier, and you can see fairly substantial deposits of it along the shore of Lake Huron, and also inland you'll find outcrops such as the one where the hammer is situated in the center there. It's Boblo again, and the beds reach about 8 centimeters of thickness. Now, this is a chert that is named after the formation. And it's got so much currency in the literature, there's not a lot of point in trying to change the name. So there it is, Onondaga chert. And it was one of the premier, if not the premier, raw material for flint knapping in southern Ontario. It's very, very popular in upstate New York, where there are also outcrops. And the outcrops run from about, well, a little village called Villanova, north of Long Point on Lake Erie. The formation swings down to intercept the north shore of Lake Erie, just east of the Grand River, and goes from there right across into New York State. And it's the so-called Onondaga Escarpment. And this material is up to 12 centimeters in thickness. Very nice working material, especially the edge cliff member, which is the basal member of the Onondaga Formation, produces this kind of chert. The one thing you have to remember is that this material, as it swings northwestward within the Appalachian Basin, does not cross the Algonquin Arch into the Michigan Basin. So unlike the Bob Lowe Formation, which does, and that's the formation just below the Onondaga, the Bob Lowe does continue on into the Michigan Basin and under Lake Huron and off into Michigan. The Onondaga does not, and that's a common misconception. People seem to think that it extends northwestward like the Bob Lowe. No, it does not. Next one's a very interesting material. Another one of my sort of, well, I guess, garbage can categories, HBL chert, Hudson Bay Lowland chert. The reason that it got that name is that when I was doing my original research in Northwestern Ontario, we were finding some very nice bifaces made of it. And we were finding that there were actual workshop sites, but they're all based on secondary materials, including some fairly substantial cobble size. Talking with people like Bruce Sanford of the Geological Survey of Canada, who's familiar with the bedrock geology of the Hudson Bay lowlands, where this material is obviously deriving from through glaciation, secondary deposits, indicated, oh yeah, well, there's chert in a variety of formations. It could be the Stooping River or the Equine River or the Severn River. And so I thought, well, we don't have any outcrops to identify. And so I guess we'll just call it Hudson Bay Lowland chert. And one of the more interesting recent discoveries or revelations, courtesy of a ROM paleontologist, David, he identified a source site on the Konogami, or a tributary of the Konogami River within the Konogami River Formation, which also kicks out some pretty good quality chert, black materials, which we also see archaeologically utilized. So there was quite a bit of excitement about that. But I just had to point out that this particular outcrop site had been reported in 1890 by Sir Daniel Wilson, who actually provided the indigenous name for the site. So it wasn't a brand new discovery. So onwards. By the way, those Paleozoic cherts that I was just referring to ran the gamut from Silurian through to Devonian, similar to Southern Ontario, of course. And here we have Selkirk chert, so-called. It occurs in thicknesses up to 6 centimeters. Lorenz Bruchert's done study, quite a comprehensive study of its distribution. It's the Dundee Formation. It lies above the Onondaga Formation. The interesting thing to my mind is, we defined it visually on the basis of a very fossiliferous fabric, as you can see, and especially in the right-hand specimen. The thing is, though, that the Morehouse member, the top member of the Onondaga, is fairly similar. So, it may be that some Selkirk chert, so-called, from the Dundee Formation, is actually a Morehouse member Onondaga chert. But then again, since they're right next to each other, that may not be such a big deal in terms of understanding movement of raw materials, etc. And finally, our latest chert in Southern Ontario caps the Middle Devonian Ipperwash Formation, Kettle Point chert. As you can see, it's quite massive. You'll see on the block to the left that there's the black Kettle Point shales. They're upper Devonian on top. And then there's a conodont hash, so-called, here infilling cracks within the chert deposit. And those are actually related to the upper Devonian shales, not the chert. And this is the upper wash limestone below. And here's a sort of typical big block hanging out of a limestone boulder, to say the least, on the Kettle Point Indigenous Reserve. You can get, as you can imagine, pieces of chert from this deposit that are up to 21 centimeters thick. One of the problems with it, though, is that this particular deposit is quite heavily jointed, as you might be able to see in the outcrop to the, secondary deposit by crane, dredging crane, to the bottom right. So it's not as lovely as it seems. One of the things about Kettle Point chert is that depending on how it's utilized or how its history in the ground in terms of groundwater impacts on coloration, it can be quite variable in color. You see this sort of blue-gray color here in this specimen to the upper left, but you can get pinks and whites and various other colors, also some of them induced by heat treatment. So the earliest MA thesis on this material was by Scarlett Genesis, and she was a Trent student. That was actually the first MA thesis committee I sat on. And it was only a mere 40 years ago, Scarlett. So adjacent United States obviously has some very significant and often later, geologically later chert deposits. And they were very important to Indigenous peoples that were living in Ontario. Bayport chert, here we have Don Simon, an absolutely incredible so-called amateur archaeologist. He's there on Charity Island in Saginaw Bay, picking up big nodules of this material, quite distinctive in coloration, banding, etc. And very much favored on sites such as Killarney Bay 1, which is an early middle woodland Middlesex complex site on the north shore of Georgian Bay. Excuse me. Another Michigan chert that has an important story to tell us is Norwood chert. You can see a very distinctive banding pattern and coloration, gray, that's characterizes this material. Interesting thing is that the Odawa were importing Kettle Point and Bayport cherts and cherts from Manitoulin into their wintering sites with the Piton in the Blue Mountain region at the south end of Georgian Bay from the late 16th century right on through until their dispersal in 1650. But very interestingly, it's only after, on sites that post-date around 1630, that we start finding this material. And interestingly, there is actually oral history which explains why this might be, but I'll leave that for another day. Of course, the famous Flint Ridge chert, various colors, very colorful at times. The vast majority of these robins blades found in caches in the hundreds is this gray, blue-gray colors is more common. You don't get a lot of the blacks, pinks, blues that also characterize the Van Port Formation. And so this is an important material that was being exported in vast quantities from quarry workshops in central Ohio. It was utilized since Fluter Point Paleo times, excuse me, but it was in the period of around, say, 300-400 BC up to about maybe 300-400 AD that this industrial scale production occurred. As I say, there are caches of literally hundreds of these bifaces scattered throughout the lower Great Lakes. In fact, as far north as northern Georgian Bay at the Killarney Bay 1 site. And so, these folks weren't fooling. They were shipping in quantity. In fact, a shipping container was actually found on Walpole Island many years ago. And again, that's another story that I'll save for another day. Wyandotte chert, very distinctive again. Very nice, easily workable material, very popular to fluted point groups, and also sort of hit a zenith in terms of use and export of bifaces in the terminal or very late Archaic period with so-called turkey tail points. And it's from southern Indiana, not far from the Ohio River, Blue River drainage oftentimes, and also on the other side in Kentucky. Muldraugh chert, another one from down in southern Indiana, not nearly so widely distributed, but this particular biface is one of the large exotics recovered from the Killarney Bay 1 site in the North Shore of Georgian Bay. It's from the same general area as the Wyandotte chert. Burlington chert, Midwest, Missouri, Illinois. Again, just huge deposits, very easily worked, responds very well to heat treatment, actually turns pink through heat treatment, quite distinctive. So I just want to use this particular chert type in the Muldraugh material also to speak to the contribution of an incredible avocational archaeologist named Jack Holland, who's no longer with us, unfortunately. He used to invite me on what he called chert chases. So together we went and visited and sampled sources in Kentucky, Missouri, Illinois, New York State, and a variety of other areas. He assembled, we have a very large reference collection at Trent University, but Jack's certainly surpassed that because when I was posted in the Western Arctic of Canada and Northwest Territories, he was in touch with me asking for samples from there. So his collection spanned all of North America pretty well when he was finished. Unfortunately, he's no longer with us, as I indicated. And his reference collection, which is extremely important, was taken and curated by the Buffalo Museum of Science. And Bill Engelbrecht, professor emeritus at University of Buffalo, was a good friend of his and great supporter through the years. Well, all of a sudden, the management of the Buffalo Museum changed, and they decided to dump this stuff. And when word of this got out, Dennis Stanford of the Smithsonian rented a truck and drove to Buffalo and loaded all his collection, his reference collection, and brought it back to Washington to the Smithsonian for safekeeping, which is, thank God for that. Anyway, full marks to Dennis again, who's no longer with us, and to Bill Engelbrecht for all that he's done for and with Jack Holland. Here's an interesting raw material. Geological source seems to be a poorly exposed, very soft, coal-rich sedimentary deposit in North Dakota and along the Knife Rivers, where there's a lot of workshops based on secondary deposits. Just to give you a sense of scale, the biface on the left, which was recovered from Southern Ontario, is the size of your hand, basically. So you can sense the size of the biface to the right. Fun story really quick about that biface. When I first worked in Thunder Bay, I went to the Thunder Bay Museum and I saw the basal portion of this biface in the collection. And I went, wow, Knife River Flint, what a beautiful piece of work. What a huge biface that must have been. And so there it sat for years and years. Was found in the Cam Delta, mouth of the Kaministiquia River, Thunder Bay. Then Bill Ross, who took over as regional archaeologist in Thunder Bay, had a gentleman come in from Florida who said, my mom used to live in Fort William, Thunder Bay, and she has this piece here, and he showed him the upper portion of this biface, which had been found in their flower garden in Fort William. And, Bill looked at it and he sort of scratched his head, and then he thought, wait a minute. So he took it down to Lakehead University, pulled out the drawer, and the two pieces fit together. I mean, what are the chances? But luckily they are together, and we can see the magnificent nature of this incredible biface. So there you go, another little narrative. So here's a material that is obviously not chert. And what it does is it speaks to other tool stones that were being utilized by Indigenous peoples in Ontario. And this is limestone, sometimes mistaken for ceramic, sometimes mistaken for, what was it, Walter called it, unfired clay at the Grimsby Cemetery, etc. Anyway, it gets a powdery surface due to organic acids in the ground. But as you can see in the bottom right, these pipes were worked out of limestone cobbles, obviously taken out of secondary deposit beaches. You see someone's knocked out an L-shaped form to begin the process of producing one of these beautiful effigy pipes. Most of them are effigy pipes. They date to the early 17th century. They're on Blue Mountain sites. That's where they were being made by Petun and or Adawa. And I'm not sure who, or maybe both. At any rate, the raw material, I've spent years and years. I know it's an Ordovician limestone. There is a similar material identified historically from Quarry Point on the east side of St. Joe's Island. And there's also, I think, more likely similar sources on Manitoulin Island, the north side of Manitoulin Island. And hopefully one day we'll nail it. Sandstone, very popular amongst Indigenous groups in Southern Ontario for the production of grinding stones, metates. Here's a fairly large one here. Greywacke, Gouganda Formation I mentioned earlier. There is one particular group who had access to Kettle Point chert and Onondaga chert, but sometimes decided to make broad points, late archaic broad points, out of greywacke. Now, I have no idea why they wanted to do that, being that this material is much more difficult to work than the cherts. Sometimes I really think they're just showing off. But at any rate, it's quite characteristic of those broad point industries, especially in southwestern Ontario, where they could collect this material as cobbles out of rapids on the rivers like the Thames and the Sauville.
So we have a question in the chat from Mona. She's asking if they could have been training spears that were kind of dull.
Oh, well, some of these bifaces do have rounded, polished tips on them, as you might sense from some of these ones down here, which may have been used in hide working. And I like, some of them are definitely projectile points, but I think a lot of them are just big knives. I shouldn't say just, but that's what a lot of these large Genesese style so-called Onondaga chert ones are. Just because they don't look particularly handsome doesn't mean they weren't napped by competent individuals. It just means that this material is so miserable that it just, again, why do it? I don't understand it. But yeah, I mean, if you're going to start to learn to flint knap, you want to give the kids some of the better quality materials to work with, because otherwise they're going to give up and walk away. Yeah, I just, yeah. But
it would have been a challenge for sure.
Yeah. Anyway, here we have a series of simple black shale pieces that have been drilled to turn them into these little pebbles into pendants. And they're derived from the Marcellus Formation, Devonian. And you can find a fair number of them on the beaches north shore of Lake Erie in the Port Stanley vicinity. And what's really interesting is when you go there on a sunny day and the waves are lapping on the sand beach and these little black pebbles are lying there, they almost sparkle in the sunlight. And it's very interesting. I have suggested that they're turned into pendants because they're symbolic of an important spiritual creature. They're, I believe, intended to symbolize the scales of horned serpents who were abundant in Lake Erie along with the great underwater panthers. So in fact, the underwater panther is where the term Erie derives from. It's a cat, and it's not a raccoon as one archaeologist suggested as the derivation of the term Erie or cat. It's the big cat that controlled Lake Erie and caused all those nasty storms, unless you're appropriately propitiating it with sacrifice and prayer. So anyway, if you walked around with one of these around your neck, it might have, protected you in some way, especially for maritime travel.
So we have another question from Jeff Percy. He's asking, was there ever much use of Reynolds chert?
Renali's chert? Well, okay. That formation only spans the Niagara River from the east in New York State, a distance I would guess of a couple of kilometers at most. There is chert, and it's the Renalis is essentially analogous to the Fossil Hill in the Silurian up north farther. And there is some chert in it, and by golly, there was an industry on the Thorold or Elijah Ball, early 17th century neutral village. And it's the only place I've ever seen that particular type of chert, which I call Niagara chert, on in an archaeological context. So during the 17th century, some of that material was utilized. I've never seen it on anything earlier. Get on to paint stones here, hematite, limonite, etc. As you can see from the colors, you grind them up, you put them in a medium like oil, and you paint them on whatever you wish, including yourself. So these materials, these minerals are important from that standpoint, and are very important, I would suggest, from a symbolic standpoint, not only on artifacts, many of which are long gone in terms of being organic, but and clothing, for instance, but on the bodies of the indigenous people themselves. So here's the banded argillite from the Goganda Formation that I referenced earlier. And it's outcrops in substantial amounts in northeastern Ontario. It was definitely transported south considerable distances as a result of glaciation. And to the top left, you can see a gorget made of this material. Very popular, is very attractive aesthetically. Particularly during the late Archaic into the Middle Woodland. Those are periods when they see the greatest use of it for production of ornamental goods. Red siltstone, yeah. This is another industry that was occurring in the Blue Mountain region on Pita-Nadawa village sites, in the particularly in the early 17th century. And you can see these pieces are slotted, and they're for the production of tubular redstone beads that were exchanged with the Huron-Wendat to the east, the neutral to the south in the Hamilton region, Niagara Peninsula region, really liked them. And they even extended in terms of exchange as far as the Senecas in upstate New York. Ohio pipestone. There's a material from down on the Ohio River. There's quarry sites on the north side, which produce this steatite-like material. And it's quite distinctive in terms of its gray-brown color. It takes a high polish, as you can see. There's even some very beautiful effigy pipes made of it. And these pipes of this material enter into southern Ontario, primarily among the neutral, again, in the early 17th century, when they're relationship with the Ohio Valley Fort Ancient peoples was quite strong, based upon a whole variety of evidence. Another siltstone, so-called, is what's known as catlinite, and that material occurs and was mined in southwestern Minnesota and made its way great distances, eastward, especially into the northeast and the southeast, in the form of pipes often, but also beads. And this is a very distinctive disc pipe form, a so-called war bundle form that came from a Piton Adawa village in the Blue Mountain region, probably dating to the earlier decades of the 17th century. And again, this material was coming into southern Ontario through the Adawa maritime transportation system, if you will, out of the Michigan Basin and up through the Straits of Mackinac, via Manitoulin, down the Bruce, around the east side of Georgian Bay, and into communities that were Iroquois agriculturalists, such as the Huron-Wendat and the Piton. We just don't get pipes of this material down farther south on the North Erie Shore, Niagara Peninsula area that were occupied by the Neutral. They were acquiring their stone pipes in disc form and various other forms, as you saw earlier, from their associates down in the Ohio Valley. So you got two different routes where these materials, these pipe stones and bead materials were transported. Chlorite schist adzes, or amphibolite adzes for Tiziana Gallo, who's been doing a lot of work recently in terms of field survey and the Shield, the Frontenac axis to the east of Peterborough and the Kawarthas. And she'll be writing up her dissertation on the acquisition and working of particularly amphibolites in the fairly near future, I believe. She's done a lot of work. I enjoyed working with her briefly in the field and trying to help out in finding sources. Another material of metamorphic nature, of course, is slate. And during certain periods, specifically the middle to late Archaic, ground slate points, typical of Archaic groups to the east, occur in southern Ontario and are very rarely distributed in northern Ontario. There are some. There's quite a concentration in the Trent Valley, the Kawarthas, and points east. I mentioned stone bead industries. Here we have a whole range of beads of various colors, steatite being worked on a Huron-Wendat Anishinaabe site. And interesting thing is using PIMA analysis of the mineral content, it turns out that this color and this color material are the same. So what this strongly suggests, to me at least, is that this naturally occurring gray steatite is being heat treated to turn it a reddish color, because the reddish color apparently is more desirable. But that's part of the famous Ball Village Site report, which will be out sometime, hopefully. Also, steatite is very important in terms of production of pipes. And this is a vasiform style, which I think is very culturally significant. And we're in the process of trying to geochemically characterize a variety of these pipe materials, steatites, trying to pin down a source for this particular material, hopefully somewhere in the Minden area, but well, I guess we'll see. It's only been eluding me for what, 4 or 5 years. What the heck? And paint stones. So here we have, I mentioned earlier about the graphite deposit in the Kawarthas. It was 100 meters away from a hematite vein. And these pieces, these graphite pieces are from the Ball site. To the north, it's a Huron-Wendat / Anishinaabe village site. And the interesting thing is they're not only producing powder by abrading the sides of these graphite pieces. This is massive graphite, which, by the way, is quite a rare expression. Most graphite that's mined and extracted is taken out of deposits that are very finely disseminated graphite. You don't get big lumps of it, such as you're seeing here. And so yeah, these substantial massive graphite deposits are quite rare. And so I feel quite confident that we've actually got the source, even though geochemically it's impossible to prove that because it's simply carbon. But at any rate, they're drilling them. And I think that's another method of producing powder. It's not because they're trying to produce pendants or beads, and none of the drill holes actually penetrate the pieces. And they're always unilateral. So I think that, again, they're grinding them with an abrader. They're also drilling them to produce the powders that they use for the paint. And here we have an igneous material, obsidian. And I guess the closest deposit is in Obsidian Cliff, I think, in Wyoming. And there's other deposits a little farther west in Idaho, of course. But at any rate, this was a commodity that was valued in the huge interaction and trade sphere of the Hopewell groups of Ohio and especially Ohio, but also Illinois. And so this piece does hail from actually the Hopewell type site in Ohio. And there was actually caches of literally hundreds of large bifaces on that site in one particular feature. So it's a massive importing of an exotic material, but that's all part of the Hopewell syndrome, if you will. And finally, we have a, well, not finally, but close to finally, we have a basalt hammerstone, and basalt being such a hard and material that has a fracture toughness is a very good material for using as a hammerstone because it won't fall into pieces very easily. You can see a modern hammerstone with a battered facet on the right-hand side there, and it's still very usable, and that's why you select basalt oftentimes for a hammerstone. Another use of these igneous materials is this diorite grooved archaic axe. One of the things I find very interesting is that this is a tough material. You can't really flake it, but you can peck it, which means you sit there with a hammerstone for days, hitting the surface and forming by little powder impacts, forming this rock into the type of tool you want. Usually it was going to be an axe of this sort. So if you imagine the amount of manpower, woman power, whatever, the amount of time that it would take to produce an item like this, why would they do that? Well, the interesting thing is that the use of these igneous materials basically terminates around 2,000 years ago. They're not doing it anymore, but they are using more friable, softer materials like amphibolite and schists to produce items which appear to be adzes. So what's going on? Well, I think what's going on is that these axes during the Archaic are being used to basically chop away at live trees. And that was a way of felling that was very laborious, but also would take a huge toll on less tough materials. And so I think there's really a transition to more forest felling, a tree felling, using the girdling and burning mechanism that was documented in the 17th, 16th, and 17th centuries, not only for dropping trees, but also for the production of things such as dugout canoes. People weren't whaling away with axes and chisels to form dugout canoes. They were lighting fires and letting the wood char and then chopping the charred wood out and working along that way. Anyway, just a thought. So, tools for chert identification. We're getting near the end, folks. So obviously, one important source for chert identification is a reference collection. And in it, you can, through your collecting of outcrops and also secondary deposits, if possible, you can come up with a whole range of color, patterning, luster, translucence, which characterizes the range for individual chert types. This is what you would see in primary deposits, where you can definitively identify the geological source, and what you could obtain from possibly the range of variation on secondary deposit pebbles and cobbles, which clearly relate to the outcrops, and also from archaeological sites. So, and what I found oftentimes is on archaeological assemblages, you're going to get a wider range of physical character for individual cherts than you'll ever see in an outcrop. And, but that's another story. So the other thing about these reference collections that should always be remembered is that you not only want to look at the raw material, but you also want to see what happens when these materials are burnt, thermally altered, or heat treated. And the reason for that is that some of them, as I mentioned a little earlier with the Burlington Formation chert from the Midwest, can quite dramatically change color if they are heat treated, or that is, they thermally altered in a controlled context, as opposed to burnt. And just as an example, in terms of coloration, if you get Collingwood chert that's been thrown into a hearth and burnt, it's going to come out black or sort of a dark navy blue in color, as opposed to the cream color of the raw material in outcrop. But if you heat treat that chert, you will get tones of pink and orange, which is entirely different than what happens when it gets burnt. And I've seen that in the case of some fluted points from the Beaver Valley and points south. Now, the other thing to point out, obviously, is that when you burn cherts, many times they'll degrade in the sense of fracturing too. And so what you'll get are very characteristic potlet fractures and crazing, none of which are particularly attractive for the use of that material. So, in fact, we had a rather interesting experience when I was down at a early chert napping workshop in Southern Illinois in Campsville. We were working with Burlington chert, and we could, bash out bifaces of fairly good size with a raw chert. And what we did is, in the evening, in a cast iron bathtub filled with sand, we would bury our biface preforms, and enter about 3, 4, 5 centimeters of sand, and then cover the sand with charcoal briquettes and fire them up. And in the morning, we'd come back, and you could clear the sand away from your bifaces, and lo and behold, they were pink colored and were more lustrous and actually worked more nicely. The basically shearing waves were better able to transit through that material than the raw material. Interesting thing was, one of the fellows opened up his biface a little too soon while it was too hot, and it started auto pot lidding, which was destroying his biface. He quickly covered it up with sand again, hot sand, and hoped for the best. But an interesting phenomenon. Always remember to let your heat-treated bifaces cool adequately before exposing them and utilizing them. Okay, so you'll also, for your reference collection, want to do some thin section work to describe the fabric, the crystal structure, and identify microfossils if possible. And in terms of recording these thin sections and the surface of the raw materials, Adrian Burke has suggested the use of a Dynalite computer attachment, and that these units are able to produce images at magnifications up to 200 times and are really, really helpful. Just nice little thing with an attachment into your computer, and using a microscope and using the Dynalite, you can get some great pictures. You'll also want to do some trace element characterization using one of the techniques we mentioned earlier, and to create an initial sort of baseline concerning the geochemistry of these different charts. And basically, if you want to communicate this information, obviously you have the option of producing digital images. And there's some really excellent reference sites in the Midwest US, states like Iowa, I believe Wisconsin has them too. And I haven't really looked around recently, but you know, they're online and they have some great images. And this is just an example of an Ohio study on a CD-ROM by Mike Kegelmacher, done in 2001. And it's got a whole raft of really valuable text and images on it, which are really helpful in understanding and characterizing Ohio charts, which are, of course, exotic to us here in Ontario. So just to finish off, I should point out that there's a volume that was published back in 1989 by the Royal Ontario Museum by Ely and Von Bitter, entitled The Charts of Southern Ontario. And it's still a standard for Southern Ontario. And but it does require updates, and with additional chart types being identified, and as a result, in part, of recent changes to the Paleozoic stratigraphy or definition. So where do we go from here? Well, I would, in fact, I've sort of been working on with Dr. James Connolly at Trent University, the establishment of a digital database of our reference collection at Trent. It's been going in fits and starts. It's not quite there yet, and I think it's partly my own fault for not committing enough time to the project. But I promise we'll get back to it and hopefully make it available. And I think it'll be an important tool for those working in Southern Ontario and adjacent states, for that matter. What else needs to be done? Well, there's all kinds of prospecting. I mentioned the Minden area steatite source. You know, we're homing in on it through assistance of the Ontario Geological Survey and Peter LeBaron and people like that in Easton, but we haven't quite got it yet. And when we do, I'll be doing cartwheels. Then we've got those Frontenac axis metasediments, and there's quite a range. Well, not quite a range, I'd say maybe 4 or 5 different metasediments. And, you know, we just don't know the source yet. And I say it could be pretty dramatic when we find them, because some of the largest bifaces from Ontario are made from these metasediments from the Precambrian deposits on the Canadian Shield. And in Northern Ontario, we'd like to continue our hematite sourcing project. Brandy McDonald did some wonderful work previously in British Columbia, mainland interior British Columbia, working with hematite sources, and then correlating rock art, pictograph sites with those sources in terms of distribution of these colorants. And she'd like to do the same thing here in Southern Ontario with the permission of Indigenous communities. But for the moment, we've already started with some characterization of geological sources. And an article was published a couple of years ago in the Journal of Archaeological Science, if you're interested. We're also working on pipestones, as I indicated. And there's steatite deposits in northwestern Ontario. There's siltstone deposits in the Superior Basin, and we just have to tie these down. There's cherts too. Again, people involved in this work are people like Brandy and Marty Cooper and Alan Corbier, who's an Adawa from Manitoulin. He's very interested in these pipestones himself for obvious reasons. David Godzala with Northern Settlement Surveys, a CRM company, who was able to nail down the banded argillite source just west of Lake Temiskaming on the Montreal River. Jeff Bursey in northwestern Ontario has been, how shall I say it, poking around and finding new, previously unknown bedrock sources, and also identifying other secondary deposits, substantial secondary deposits of the infamous Hudson Bay Lowland chert. And there's other interested individuals who've contacted me about sources around Lake of the Woods, which may help us to finally do a better job of defining the sources and distributions of these materials. So on that note, I'll just complete my presentation.